In the last lecture, we dealt with Kirchhoff's laws. As you might know now, that these laws are an easy way to calculate currents, voltages, resistances in the various components of an electrical circuit. Today, we start with magnetic effects of currents, and we shall find out the magnetic field of currents in various shapes. You are familiar with magnets. Most of you might have even played with them. Every magnet has two poles. An important fact to remember is that no magnet has ever been found with one pole, or an isolated pole called a monopole. This implies that whatever the conditions, each magnet must have two poles. If we cut a magnet, the two portions of that cut magnet also have two poles each. Even at atomic scale, an elementary magnet has two poles. This is in complete contrast to electric charges, which can exist in isolation. I mean, you can have positive charge, you can have a negative charge, but here each magnet must have both the poles. You can't have an isolated pole or a monopole. For practical purposes, however, poles at the end of an extremely long bar magnet, you have two very long bar magnets, and these two can be considered as isolated poles, and then the force between them is given by this. The force of attraction or repulsion between magnetic poles is similar to the Coulomb force between charges. Here also, like poles repel each other and unlike poles attract each other, and the force between the two poles is mu 0 by 4 pi into m1 m2 by r squared, where m1 m2 are the strengths of the two poles and mu 0 is the permeability of free space or vacuum. Remember that mu 0 and epsilon 0 are related to each other through the velocity of light. C is equal to square root of 1 by mu 0 epsilon 0. Remember, epsilon 0 we used in the electric field. An important property of a magnet is that when suspended freely, it always north south direction. That is, if I take a magnet here, then suspend it freely, then it will always settle in a direction which is north south, which points towards north and towards south, as shown here. The pole which points towards north is called the north pole of the magnet, and the pole which points towards south is called the south pole of the magnet. Remember, each magnet must have two poles. It cannot have one pole. It is this property of settling in the north south direction that made a magnet a navigational aid for travelers on land and on sea. You see, in ancient times, you could find your way, you could find your direction with the help of magnets. That is why they were called navigational aids. For this purpose, a small magnetic needle is mounted on a pivot so that it can rotate freely in the horizontal plane. Such a needle is called a compass needle, and you must have been familiar with these needles. Strictly speaking, a freely suspended magnet points in the magnetic north south direction, not geographic. You see, here I have shown both the directions. The north south direction, which is geographic, is the actual axis of rotation of the earth. The magnetic axis, here is a magnetic north and magnetic south. This line joining the magnetic north and magnetic south is called the magnetic axis, and this makes an angle of about 11 degrees with the north south direction. This angle changes with time, but at the moment this value is about 11 degrees. Like the force of attraction or repulsion between charges, the force between magnetic poles is explained in terms of a field. In this case, we call this field a magnetic field. We say that a magnet creates around itself space or magnetic field, in which if another magnet or a current carrying conductor enters, then that body which enters will be affected by this field. This is called the magnetic field, and magnetic field is represented as electric field by what are known as magnetic field lines. It must be remembered that the field lines are only imaginary lines. No such lines actually exist. They are used simply to map a given magnetic field. The following are some of the properties of the magnetic field lines. A field line starts at a north pole and ends at a south pole. Here it ends at a south pole. This will also end at a south pole, and inside the magnet these lines go from south to north, so that these lines they form complete loops. That is important. We shall see why they form complete loops, but for the moment remember they form complete loops. At any point on a field line, if I want to find the direction of the magnetic field, I draw a tangent at that line, and the direction of the tangent gives you the direction of the magnetic field at that point. The relative density of field lines, it dictates the strength of the field. These lines, for example, and these lines are denser than these, and therefore this field is stronger than this field. Straight and equally spaced lines indicate a uniform field. These lines are parallel and equally placed, therefore they represent a uniform magnetic field. Another important property is that there is tension along the length of field lines. If this is a field line, then this field line acts as a stretched spring. That means, if I leave it, it tends to come back. So, they always tend to shorten their length, and in this process they cause attraction between unlike poles. Here I have drawn magnetic field lines of two poles, two bar magnets, south pole here, north pole here, and the lines go like this, and these lines tend to shorten their length, and therefore there is this force of attraction between the two magnets. Also, the field lines exert lateral pressure, that is sideways pressure, and this results in the repulsion of two like poles. Here I have got north pole, lines go like this, lines go like this, and wherever they are in the neighborhood, there is repulsion, there is pressure pulling them apart, and this gives rise to repulsion between like poles. Let us learn some history. In 1820, the Danish scientist Ørsted showed that a magnetic needle kept in the vicinity of a current carrying wire gets deflected. This may be common knowledge today, but it was first discovered in 1820 by Ørsted. This was a clear demonstration that the current carrying conductor was behaving like a magnet. That is, if you have a conductor which carries current, then it behaves like a magnet. Remember that at that time the only magnets known were the natural magnets, lodestones, or made from iron. So, the fact that an electric current could be a source of magnetism was a very important discovery. Following Ørsted, the French scientist Ampere performed a series of experiments with current carrying wires. He showed that the magnetic lines of force form loops, we shall see that in a moment, loops round the wires which carry current. He also explained the sense in which the loops of field lines are wound round the wire, and then the direction in which they are wound. We shall find that in a moment. The field lines follow what is known as the right hand thumb rule. That is, if I take my right hand and stretch my thumb like this, this is the direction of the current, then the way these fingers are wound, that gives the direction of the magnetic field lines. As shown here, stretch your thumb of the right hand, then you see how the fingers are wound, and that gives the direction of the field lines as shown here. Following the discovery of the magnetic field due to a straight current, Ampere argued that two straight wires carrying parallel currents would attract each other, while those carrying currents in opposite directions would repel each other. You see, these are the two wires carrying current in the same direction, there is attraction between them, and here are two wires carrying current in the opposite directions, and they repel each other. Ampere also proposed a law known as Ampere's circuital law, which enables us to calculate the magnetic field due to current sources. You see, we have seen that currents are sources of magnetic fields. So, Ampere proposed this law, which allows us to calculate the magnetic field due to various currents. The law states that the line integral along a closed loop over the component of magnetic field parallel to the loop is mu 0 times the total or net current passing through the surface S spanned by the closed loop. Let me explain. I have a loop C here, I have a loop here. This loop spans a surface, and the currents are going through this surface this way or that way. And if I take the component of magnetic field parallel to the direction of the loop, then the integral B parallel over this loop gives us mu 0 times the sum of currents which are passing through this surface which spans this loop C, explained here in greater detail. You see, B parallel is the field, B is the field, and B parallel is the field which is along the direction of the loop. So, B parallel times d l, the integral of that, the line integral of that is equal to mu 0 times the sum of the currents I 1 plus I 2 plus I 3 etcetera, which are passing through the surface S. In the present case, after taking due account of the directions of the currents specified by the anti-clockwise direction of the loop, you see, we have to determine which current is positive, which current is negative, because we said algebraic sum of currents. How do you find that? We use the right hand thumb rule, and here this loop C is in the counterclockwise direction, therefore, the current in this direction is positive, the current in this direction is negative. So, I 1, I 2 are positive currents, I 3 is the negative current considering the direction of this loop. That is very important, that you apply the right hand thumb rule, find out which currents are positive, which currents are negative, and then in this case this sigma I gives I 1 plus I 2 minus I 3, and mu 0, let me remind you, is the permeability of free space. Its value is 4 pi times 10 to the power minus 7 T m a minus 1. In vector notation, Ampere's law is written as B dot d l. B dot d l is obviously the parallel component. So, therefore, B dot d l is equal to mu 0 times I enclosed, all the currents which pass through the surface enclosed by the loop. This law is the magnetic analog or counterpart of the Gauss law in electrostatics. Let me remind you, Gauss law in electrostatics was B dot d s, where d s was the element of the surface, and B dot d s is the flux through this element of the surface. So, the total flux, that is the integral of B dot d s, is equal to q, the charge enclosed within that surface, divided by epsilon 0. The evaluation of the integral in Ampere's law becomes easy if there is some symmetry in the system. Recall that for Gauss law also, for the application of Gauss law also, we needed some symmetry. So, here also we need some kind of symmetry to make it possible to apply Ampere's law. Let me immediately take an example to fix the ideas of these loops. I have three currents, this blue one and two red ones. The red ones are coming out of the plane and the blue one is going into the plane, and I have got three loops here, C 1, C 2, C 3. So, let us take the first C 3. C 3 is anticlockwise and therefore, the current going into the plane is a positive current. Therefore, if I take loop C3, then integral of B dot dl in that loop is equal to mu 0 times I. For the loop C1, B dot dl is equal to, for the C2 this loop is clockwise, and therefore, the currents coming out of the plane, they are positive currents. Therefore, B dot dl is 2, because there are 2 currents, equal currents, 2 mu 0 I. And let us take the third loop. Third loop is, we have dealt with C3, C2 and C2. C2, there are 2 currents which are equal and opposite. Therefore, the net current is 0. Therefore, for the C2, B dot dl is equal to 0. For C3, B dot dl is equal to mu 0 I. For C2, B dot dl, integral of that is 0. For C1, B dot dl is equal to 2 mu 0 I. The important thing is that considering the direction of the loop, you must find out the positive direction of the current. What happens in the above problem, if the loop C3, for example, is clockwise? Let me show you loop C3 again. C3 was anti-clockwise. Suppose I make it clockwise, what happens? Then this current becomes negative. With respect to the direction of the loop, this current becomes negative, and therefore, the integral of B dot dl becomes minus mu 0 times I. So, every time you have to determine the direction of the current, whether it is positive or negative, considering the direction of the loop. As an application of Ampere's law, let us find the magnetic field due to a straight current at a distance r from it. So, I have a straight current at a distance r from this current, I want to find out the field. Remember that I am taking a very long straight current. In fact, theoretically it should be infinitely long. If it is so, then there is symmetry all around the current, except at the points near the ends. So, we are not worried about the ends, we shall take somewhere far from the ends. There is circular symmetry also, because there is a straight current, therefore, there is a circular symmetry. So, with these 2 symmetries, the longitudinal symmetry and the circular symmetry, let us see what we get. We take this current, and we have seen already from Ampere's work and from Oester's work that the field lines would form a loop. So, let us imagine there is a loop, and this loop is drawn with the radius r, the distance at which we want to find out the field, and then this loop, considering this current, I have taken this loop to be in the anti-clockwise direction, again using that rule. Because of symmetry, the magnetic field must be constant along this loop. It cannot be across that loop, because then dot product becomes 0. So, it must be along the loop and must be constant because of symmetry. Therefore, I have got the Ampere's law, B dot dl is equal to mu 0 I enclosed, and I use that law. This, the length, total length of this loop is 2 pi r. So, 2 pi r, you see in the integral B dot dl, B is constant, so I can take it out, and integral of dl is simply 2 pi r. So, we have 2 pi r b is equal to mu 0 I, which gives B equal to mu 0 I by 2 pi r. So, the magnetic field due to a current, straight current, is equal to mu 0 I by 2 pi r at a distance r from the current. And again, I have repeated it several times, you can find that if the current in this direction, the loop must be anti-clockwise. Let us take another case. Suppose a solid cylindrical conductor, we took a wire, suppose there is a rod of a certain thickness, and let us find out the magnetic field due to that rod. So, what we do is, this is the cross section of the cylindrical conductor of radius a, and I draw a circle of radius r inside this cylindrical conductor. Remember that the current is uniformly spread along this cross section. Remember that. So, as the magnitude of the current is proportional to the area of the cross section, is uniformly spread, therefore, it must be proportional to the area of the cross section. Then for radius a, whose area is pi r squared and the total area is pi a squared, therefore, the current through this area spanned by this radius r is I r equal to I times r squared by a square, simply proportional to the area for r less than a. Now, you consider the loop of radius r, and what we do is we again, because of symmetry, the magnetic field must be constant. The integral of d l in this case would be 2 pi capital R. So, 2 pi capital R times B r, the magnetic field at a distance r from the center of the axis of the cylinder, that is equal to mu 0 times I. Therefore, B r is mu 0 I by 2 pi a squared into r. I here is I r. Remember, I r is I r squared by a squared. Therefore, 2 pi r B r is equal to I r times mu 0, and therefore, B r is mu 0 I by 2 pi a squared times r. What about the field outside? At the center r is 0, this radius is 0, therefore, field is 0. At the boundary r is equal to a, r is equal to a, therefore, 1 a gets cancelled, and therefore, B r becomes mu 0 I by 2 pi a. So, it becomes mu 0 I by 2 pi a. At r greater than a, the whole current is included, therefore, the application of Ampere's law simply gives you B equal to mu 0 I by 2 pi r, which again is all right if I put r is equal to a is the surface, and r greater than a, all the current is included. Therefore, 2 pi r times B is equal to mu 0 I. Therefore, at a distance r is equal to B is equal to mu 0 I by 2 pi r. If I put r equal to a, then I get the magnetic field at the surface of the cylinder, which matches with what we have found earlier. Here I am showing the profile of the magnetic field. We have got magnetic field here. This is the radius a of the cylindrical conductor, and this is r distance outside the radius, and this varies as 1 by r. We have found that the magnetic field outside varies as 1 by r. Therefore, this is 1 by r curve. This is a straight line which shows that within the cylinder the magnetic field is proportional to r. So, therefore, we have got magnetic field directly proportional to r, linearly proportional to r, goes up to a, and then the field decreases by 1 by r. We just found that. So, by use of Ampere's law, we have been able to find magnetic fields due to a straight current and also due to a straight cylindrical conductor. In the next lecture, we shall continue with the Ampere's law, and we shall also find the fields due to a solenoid.